Okay, everyone, this video is going to go over the dependent samples t-test. It's known in the book primarily as repeated measures, but as I was saying in the last video, it goes by a number of different names, even though it's the exact same statistical technique. We're just going to take a look at what it is. I need to describe what the null hypothesis is, since this is a two-sample test. We're going to conduct one by hand. Actually, I've just typed it up for you. And then I want to talk about interpretation. Along the way, I want you to be thinking about some alternative methods too. I'm going to talk about where decisions come into play, where things could have happened differently. So that's just something to think about as we go through this. For the background, I want to remember that we had the hypothesis in class before classes went online that stair climbing would increase heart rate. And so I wrote just a quick blurb there in APA style describing what we found when we did stair climbing studies in class. We did a one sample t-test. Before we get into the stats of this, I want to point out something that is more like a research methodology, and that's that our study had a confounding variable. So confounding variable is something that you'll hear talked about a lot. In fact, you'll read about it in the article assignment this unit. A confound is a variable that also distinguishes between your sample and the population, or between two samples, and they're not your independent variable, but they might be causing some kind of confusion. And that's kind of abstract, so let me show you this one. Like in a drug trial, when we test drugs for FDA approval and things like that, there are two big confounds, which means that the people who take medicine both have the passing of time and the belief that one is getting treated. So the way that would work in a study is that your general population might take a drug. Later on, we'd measure the symptoms, and any change in symptoms we could attribute to the treatment. But it also could just be that they got better over time, or it could be something about the belief that they were getting treated helped them. And it's been shown that things like reduced stress, taking better care of yourself in terms of diet and exercise, those are all associated with treatment belief. So what we do in experiments is we create another condition, and that makes this the independent variable. It can vary between being a treatment, which is a drug, or a control condition, which is a placebo. And it gets the name control because it's controlling the confounding variable. So at the end of the study, both groups can be measured. Both groups will have a combination of time and belief. Only this group has the treatment. And so by doing that, you get rid of the confounding variables of time and belief, and you can compare treatment to non-treatment. Well, we have a similar problem here. If we go back to our study, we see we have a stair climbing group that had change in heart rates. But we compared that to an idle population, and there are other things happening beyond just the stair climbing. You have to bear with me here. The confounding variable that jumps out to me most is that there was a change in altitude. Okay, and altitude is kind of important to heart rate. I looked this up on the internet. It's a very useful thing. It turns out that at sea level, effective oxygen is about 21%. That has to do with the amount of oxygen that you are able to breathe and use in your environment. Now, as one goes higher up, that value goes down. So I looked at Denver, for example, and rather than being 21%, it's all the way down to 16.5, which means you have to work harder to get the same amount of oxygen in your blood. So we can't rule out the fact that the stair climber groups in our class had a higher mean than the population because of the change in altitude, unless we do a true experiment. So I'm proposing that we do an experiment where we have a treatment group go up some stairs, and then we'll measure their heart rate. The control condition, they're going to go in the elevator, so they have the exact same change in altitude. That's the confounding variable that we're controlling. But they don't get the treatment, which is the actual stair climbing. So what I did is I got my kids to do this, and they went, son went up the stairs first, took his heart rate, daughter did the elevator first and took her heart rate. And I did it, and then we had a neighbor do it, and everybody was staying really far away from each other, so we were being safe. And so that was the format of the study we did. Now, the reason I think we can analyze it with a dependent samples t-test is because I have my score for the elevator and my score for the stairs and for the others in the study as well. So here's how we're going to set this up. In a test, you start out with a null hypothesis. Our null hypothesis in this case is going to be a mean difference is equal to 0. And I want to show you what this looks like in step 3. What we're going to do is going to put a before and after, or stairs and elevator, might be a better way to think about it, and we're going to get the difference. And if there was no difference between my heart rate in the stairs versus the elevator, that difference will be about 0. We don't always expect it to be perfectly 0 because of sampling error, but it'll be close. And so what we're going to do is calculate the average difference for each of the people in the study, and we're going to see if it's different from 0. All right, let me go ahead and show you the rest of this, and maybe you can pause and jot some notes down, then we'll work through an example. The critical value says that this distribution has a mean of 0, and it has n differences minus 1 degrees of freedom. So however many different scores we have minus 1 will be our critical value for t, or degrees of freedom. When we calculate the test statistic, we're going to start with the differences. After the differences, we ignore the real scores, the early scores, and we're just going to be thinking about what we're doing in terms of change or difference. We're going to need mean, standard deviation, and standard error of the differences. And that's because our t-test looks like this. So our t-test says we need the mean of the differences minus the null hypothesis mean, which is 0. Now when you're actually doing this, you don't have to write down minus 0, but you should know that that's what we're doing. We're comparing our differences to 0. And then that's the standard error of the difference. So to find standard error of the difference, we need to go through a couple things, or 3 things. First is the sums of squares, which we'll use to get standard deviation. We'll use standard deviation to get standard error, and then put the standard error in there. Finally, we decide if we reject, we think about type 1 versus type 2 error, and we make some kind of judgment about the size. So if you want to pause that for a second, make sure you understand those things, and we'll run through an example using my heart rate data. Okay, so we have here the, this is going to be a dependent samples t-test because it is a repeated measures study. It looks at individuals in both experimental conditions and compares one score to the other. So I'm going to write the mean difference is going to be 0. In other words, each of us will have no difference between our stair heart rate and our elevator heart rate. Now, the alternative is usually that these things are not different. But if you think about this, I actually really seriously doubt heart rates would be lower in the staircase condition, in the staircase condition. In other words, I have a pretty good idea that there's going to be a difference. And when you have a good reason to suspect a certain difference, you can create a one-tailed or directional hypothesis. So if you remember the discussion of effect sizes of power, remember that you can say, I don't think it's going to be different. I think it's going to be greater than or less than. Now here, I'm going to go with this because that gives me a little bit more power. We haven't done one of these yet, so it'll be interesting to see. Now, in doing that, I just want to call your attention to this. In a repeated measure study, you have before minus after, or after minus before. You have to think about which way it works. I came up with this because in my head, I'm thinking I'm going to have stairs minus elevator. Stairs should be a big number, so minus the elevator should give me a positive number. So that way, when I'm looking at positive numbers in my data, I'll know that means that's how much more the stairs caused. But that's really your decision. Okay, so for the critical value, it's degrees of freedom for the differences minus 1. I actually wound up with 5 people at the end of this. So what I'm going to do is look at the one-tailed section of my t-table. Last time I showed you this, we went with 2 tails, but this is the one tail, and there's the 0.05 column. I have 5 people in my sample. Those two come together right there at 2.132. All right, so I'm going to come back to working the problem. My critical value is right there. T critical, 4 degrees of freedom, is 2.132, and that's a positive because I expect my mean will be greater than 0. All right, so here are the data we have for the 5 of us. It's my kids, me, and 2 neighbors. The first thing we're going to do is find differences. And remember, I said that I'm actually going to do this with the elevator scores here and the stairs here. So I'm doing it that minus that. So that's how I chose which way to do it. I put the bigger number first because I want to think positive numbers represent an increase. All right, so I got 16 there. For the next row, 28, 14, 28, and 20. So my differences are right there. Now I'm going to just ignore those from now on. I'm doing a test comparing those on average to 0. All right, so I have a new screen here because I have to do several calculations here. And what I'm going to do is going to set this up in a way that makes it easy for me to calculate sum of squares. If you remember, the t-test formula requires us to find standard error, so I'm going to need standard deviation, so I'm going to need to get sums of squares. So I have my little cheat sheet, and I put it in the order that I'm going to work through it. So, finishing out the scale, I cheated and used Excel, but I got those numbers, plugged those in here, got 172.8, and if you need to stop and look, hit pause. Brought that number down here. N minus 1, I have a sample of 5, so that's 4. My standard deviation then is 6.57. My standard error is 6.57 divided by the square root of n, so that's 2.94. And so my test statistic is the mean difference. Here are my differences. The mean difference is 106 divided by 5, 21.2. So over my standard error, which is 2.94. So my t-test is 7.21. Final step, get to make my decision. My critical value is 2.132. My test value is 7.21, which is much higher, and therefore I can reject the null hypothesis. I'm going to reject the assumption that nothing has happened and say, yes, my mean probably does come from a different group. Stair climbing probably does increase heart rate more than the elevator does. So I think I've done a pretty good job of showing that altitude is not causing this. And one of the things we'll need to do next, though, is to find out if this has a big effect. So again, Cohen's d tells us if it's a big effect or not. The mean difference, again, that's my total difference divided by 5. So the average difference score is 21.2. My standard deviation gets rid of the sample size. That was 6.57. That's a 3.23. Remember, that goes on a scale of absolute value. By the time you get to a Cohen's d of 0.8, 0.9, 1, you're starting to get a pretty big Cohen's d. So this is actually a huge one. This means stair climbing has a really big effect on heart rate. And then finally, the last thing I have down there is the written description.